Welcome to One Chemistry. Always try to do your best. Now, let us see about 100 conversion in organic chemistry. We are seeing it as episodes. This is the episode number 76. If you didn't watch the previous episodes, I encourage you to go and see. Here, we solve 5 problems step by step. Stay tuned. Let us see the question number 1. The starting middle is a 6-member system with alkene and one epoxide in the second position. Then you have organocopper and you have zinc copper couple and methyl halide. They ask you to find the product. Definitely you might see the products are ring is open. The epoxide open to alcohol and stereochemistry also specified. Then the methylation occur at the double bond also. The question is all about alcohol position, methylene position and methyl position. Whether they are above the plane or syn position or anti position. So stereochemistry also specified here. So from the reagent zinc copper couple, you might understand the naming reaction. Then stereochemistry definitely played the role here. The answer is A. Let us see how. The starting metal contain alkene, you are using the copper lithium. Nearby that you have strained ring there. What really happens is methyl attacks, ring will be open. Normally this kind of system, methyl will attack an axial form. It will lead to the chair conformation. So always axial attack is favorable here. Then the ring is open, alcohol is formed. During the course of the time, double bond shifted. So we redraw the double bond again to the center position. So methyl and OH are trans to each other. Then you have zinc copper couple and methyl diiodide. So you got the epoxidation there. This reaction is methylation reaction. This is called Simon-Smith reaction. What really happens is double bond get methylated and it is coordinated by the zinc there. So it's a guided methylation. It is guided by lone pair of electron in the oxygen. So zinc anchored with oxygen, it forms above the plane. Since OH is above the plane, the product cyclopropane also above the plane. So if you draw perfectly, you got the product A. Methyl is above the plane, OH is above the plane, CH3 is below the plane. Here you have to learn 2 important things. One is axial attack. Axial attack is very much important in terms of cyclohexene. If you attack in the axial position, you have the chair form. Otherwise you have unstable twisted boat form. Then Simon-Smith reaction. The Simon-Smith reaction normally used for methylation of alkene. So here guided methylation occurs through the alcoholic group. Then the question number 2. The starting middle is the acetophenone, you are using samarium iodide. Then you are using the alkene with ester group there. They ask you to find the products. There are the 4 products. 4 products are having the different possibilities. Whether the cyclization with 6-member ring or 5-member ring or just O-methylation or the continuous addition there. From the samarium reagent, you might understand it's a special reagent. And ring closure is occur or not is the real question. The answer is D. Let us see how. Here starting middle have carbonyl group, you have samarium iodide. Samarium iodide is a special reagent. It's a 1 electron reducing agent. It just donates 1 electron. So what really happens is the carbonyl return as diradical, the samarium donates, you have the negative charge at carbonyl. You have 1 free electron, it's very unreactive. Then you have carbonyl and double bond. Obviously you might expect the carbon-carbon bond formation. Here the driving force for this reaction is the radical instability. It forces the carbon-carbon bond formation, so it forms. So O- is there and ester carbonyl group is there. So intracondensation occur, new 5-member ring form. 5-member ring with oxygen. So it is the final product D. If you rewrite properly, you get the desired answer, which is D. So here you have to learn 2 important things. One is samarium iodide, which is a Cahan's reagent. The reagent actually give 1 electron for reduction. Then whenever you have negative charge and ester group, you might think of intracondensation. Here methoxy group leaves, new 5-member ring is formed. The driving force for this is ring formation. Then the question number 3. The starting metal is octadiene and the dienes are in the separated symmetrical position. You have acetyl chloride and aluminum chloride. They ask you to find the product. The products are mostly what happened to the double bond is the question. If the double bond is happening, or alpha position reaction happening, or ring expansion, ring contraction is occur or not is the question. So obviously the question is about ring stability versus reaction. The answer is C. Let us see how. Starting middle you have chlorine, you are using the aluminum chloride. So it's a kind of Friedel-Crafts kind of situation. So you have acyl cation, you have cation, you have diene. So you might think of the direct interaction between diene and cation. So what really happens is the ring instability promote the intra-cyclization or intra-fusion. So what really happens is trans-carbon assist, the 4,8 or 5,1 attack, both will be the same. It will have bicyclic ring formation. So you have carbocation at the 5th position. The cation again quenched by the chlorine there. Here you have to learn two important things. That is, whenever you have large ring, you might think of the ring contraction, because if the ring is larger, the stability will be less. The second thing is trans resistance always helps in the reaction because it's sterically perfect position. Here 4th carbon attacks 8th and promote the 5-member bicyclic product. Then the question number 4. The starting metal is 6-member system with conjugated ketone and ester group is attached there. You are using the base and ethyl bromide and ethyl lithium. Finally, you are doing hydrolysis. They are given the 4 products. All the 4 products are different in the ethylation, where ethyl attacks the carbonyl carbon or the double bond, or what happened to the double bond switches, or ethyl attacks at the 2nd position is the question there. So obviously you have to think of reagents, and regioselectivity of ethyl addition is the real question here. The answer is A. Let us see how. So you have the starting metal with alpha hydrogen. You are using the bulky base. The bulky base abstract the proton at the alpha carbon. You have the carbon at 3rd position. So ethyl bromide attacks, it form at the 3rd position. Here no confusion, because base is drives the reaction, not ethyl drives the reaction. Here you are using the ethyl lithium. Ethyl lithium is the harder product. Definitely it attacks the carbonyl. So you have the carbonyl ring attack. You have alcohol formation. Then if you do hydrolysis, you have the 2 things happening. One is the ketone formation. One is the acidification of OH. It forms as a double bond, and the double bond moves. You have the ketone there. So the product is clearly A. Here you have to learn 2 important things. One is the driving force. Whenever you think of reagent, don't blindly think the product. Think of the possibility and bulkiness of the reagent. Here first step influenced by LDA, which is bulky base, abstract the alpha proton. Second step, ethyl generated from ethyl lithium is harder, so it directly attacks the carbonyl there. So you have to think of the reaction and its driving force. Then the question number 5. The starting metal is 10-member system with carbonyl and thiophenol at the 2nd position. You are using the CBBA 1 equivalent, and you have acetyl carbons and you have base sodium carbonate. Here 4 products are given. 4 products are such as ring expansion possibility and the double bond forming possibility and the dihedron forming possibility. Products are a little bit different. Definitely carbon skeleton and bonds are moved here. So from the reagents and reactant, you might guess naming reaction is involved, and the fate of sulfur is the question here. The answer is D. Let us see how. The starting metal you have thiol. We are using CBBA. People are thinking of CBBA as a bare-Villiger oxidizing reagent. Here bare-Villiger oxidation is not possible. Why? Because sulfur has high affinity for hydrogen. So sulfur attracts the oxygen, it forms sulfoxide. It's a just oxidation there. Then you have acetyl reagent. What really happens is O acetylation happen. CH3CO attached to the O. Then the next step, CH3COO is a very good leaving group. It removes and you have alkene there in the product. So acetyl group remove and added to the directly to the carbon. The same group go from S to carbon. It's a rearrangement there. Then the next step, you are using the sodium carbonate. Sodium carbonate, what really doing is it forms the O- and remove the PHS there. So it removes the thiol, which is phenol analog. Then you have dihedron there, which is answer D. So multi steps but simple concepts. Here you have to learn two important things. Whenever you have sulfur among the ketone, you might think of sulfur oxidation, not pair-Villiger oxidation. Then the next thing is fumarate rearrangement. Whenever you have sulfur system with asteryl acetate, you might think of the rearrangement of asteryl group within the system. That's all from this episode. I hope it was easy. Thanks for watching. If you have any suggestion, comment below. Stay tuned for next episode.